supply points. The total inflows into our demand points are equal to the total requirements for those demand points. The total inputs or the net inflow into our transshipment points are equal to the demand requirements at those transshipment points. So those are the three sets of constraints that we need, in addition to the linearity assumption and the non-negative assumption, which we're going to fill out in the options. Okay, so let's go into Solver and work with this. So this is the cell that we're trying to minimize. My changing cells are B's. I'm going to add my constraints. First of all, my supply outflows need to be lesser than or equal to my demand capacities. Add that one. Secondly, my demand inflows need to be equal to the demand requirements at my demand points. We've added that. And lastly, my net inflow into the transshipment points needs to be equal to the demand requirements of those transshipment points. So those are your three sets of constraints. In your options, just assume linear, assume non-negative, should be checked. And let's solve this. And it did not work. Okay. So Solver did not actually do what I thought it would do. Let's see what actually ended up happening. The total cost comes out to 0 for some reason, and it looks like everything is being supplied from the dummy node, and I think I know why that is. Because one of the constraints that I forgot to mention is that our dummy node, which is also part of our supply node, cannot supply more than 25 units. So we've put that into our data, but I forgot to put that into my constraints for Solver. So let me just do that quickly and resolve again. So let's go into Solver and add one more constraint, which says that my total outflow from the dummy node, which is this cell right here, needs to be lesser than or equal to the supply capacity for the dummy node, which is 25, which we already set up, but I just forgot to add this constraint. So let's add that one constraint. Our options are still fine, and let's solve for this now. All right, and now we get a solution. So that's your total cost then. Let's just eyeball the solution to make sure everything's okay. Yeah, it's using the routes that we've assigned. It is not using any of the routes that have a high cost associated with it. One thing which might stand out to you is that one of the outflows is 94.9999 instead of 95, but it's basically 95 units. It's not using integers, but if we wanted to restrict it to integers, we could do that. But yeah, ultimately this is using 95 units out of Bangkok being supplied to Chicago. That's what this row is showing you. So if you look at your dummy row for the flows, then there's a flow of 25 to Sioux Falls, which means that Sioux Falls is the demand node which is going to be short of 25 units. So that's going to be the demand point that will be short by 25 units. And that is the information that's being shown to you in your model in the dummy node itself. Your total cost, like it says over here, is $361,000, 530. So you have your total cost. You've satisfied the demand for the three demand points, 80, 78, and 55, except that for Sioux Falls, the 55 units that are coming to Sioux Falls includes 20 from Sacramento, 10 from Chicago, and 25 from the dummy node, which means that this is the node that's going to be short by 25. All right, so that solves our model, and we know what our total cost function is going to look like, which node is going to fall short, and I hope this is clear to you. I will again post the spreadsheet online with some instructions so that You could use that spreadsheet as a template for your assignment as well. All right, so I'm guessing by now you've gone through multiple problems using Solver, and we've seen how Solver can help us in optimization problems where you have a linear programming approach to the problem. However, Solver can also be used to solve nonlinear problems, and these are problems where you're not going to check mark that assume linear option in Solver. We are not going to delve too deeply into these nonlinear problems, except one example that I do want to show you, which is related to something we've talked about before, and that's your facility location problem, which can be solved by using a nonlinear approach as well. So this was one of the problems that we've seen before, where we had 5 retail outlets. We were given the X and Y coordinates of those 5 retail outlets. We were also given the volume of material movements in those retail outlets, and we were going to look for a warehouse which would be located at an optimum location to be able to serve these retail outlets as effectively as possible. So that was the context of our problem, and we saw how to use the centroid method for it. And again, if you recall, the centroid method simply is a heuristic approach, which you are just going to use a manual formula for. And again, the idea was that you're going to take the sum product of your X coordinates and the volume of material movements and divide that by the total volume, and take the sum product of your Y coordinates and the volume, divide that by the total volume. And that would give you the X and Y coordinates for your centroid. So that is one approach, which is a good starting point. But if you want Excel to find the optimum location for you, you could use Solver for it. For that, we are going to use the concept of what's called the load distance metric in supply chain planning. And it's a metric that is very commonly used in network planning. The one additional thing that I'm going to give you in this context is the formula for straight line distance between 2 points. So if you have a point x1, y1 and a point x2, y2, then the distance between those points can be measured by using this formula, which simply says take the difference between the x coordinates squared and take the difference between the y coordinates squared, add them up and take the square root, and that gives you the distance between 2 points. And the load distance metric then simply is the volume that is going to be transported on that route and the distance of that route, the product of those two things. So the product of the volume of transportation on a route and the distance of that route. That gives you the load distance. So what we can do then is, using Solver, we can come up with a solution which tries to minimize this load distance for us between all of the retail outlets and our warehouse. So what you want to do is you want to get an as efficient solution as possible, so try to reduce the total load distance of your entire problem. So we can do this, and let me just open up Excel and try this out. So this is the data that I've been given, exactly from the slide that I showed you, the X and Y coordinates of the 5 retail outlets, the volumes. The warehouse location is what we want Solver to tell us. So I'll just shade these as red because Solver is going to fill these cells for us. What we do need in our model then is an idea of, or is the actual distance between this warehouse location once we find it and the other retail outlets. So I'm just going to copy all the retail outlets into here, and the distance between outlet and warehouse is what I'm calculating here. So again, that distance simply, if you remember, is the square root of the difference between the x coordinate and the y coordinate squared plus the difference between the y coordinate of the warehouse and the y coordinate of the retail outlet squared. All right, so that will give you the distance between retail outlet 1 and the warehouse location. What I do need to do is for the warehouse location itself, I will need to make that into an absolute reference so that that does not change. And I could just copy the formula over to the other retail outlets. Okay, so that's your distance between the warehouse location and these retail outlets. Your load distance metric is simply going to be now the sum product of the distance and the volumes that you have. And this is what you're trying to minimize using Solver. All right, so let's do that then. So let's get Solver to help us with this. And I'm just going to reset everything in Solver. So this is the target cell that I'm trying to minimize. That's the load distance metric. The cells which are going to change, or the cells which Solver is going to recommend values for, are the X and Y coordinates for the warehouse location. In this case, there really are no constraints that you've been given. There are no limitations on what these X and Y coordinates can be, or any of the other limitations that we're aware of. So we'll leave the constraints to be empty. For the options, we normally choose assume linear and assume non-negative. That's what we've been doing so far, because most of our problems were linear problems. In this case, if you consider the formula that we're using for calculating distance, that is not a linear formula, because there are powers, and that we're using squares and we're using square roots, so it's not a linear problem. Also, I'm not going to checkmark assume non-negative, because on the XY plane you can have negative coordinates as well. So I'm not going to choose any of those options, and I'm just going to click OK and click solve and see what happens. So in this case, it's given me some coordinates. It's suggested 12 for the X coordinate and 15 for the Y coordinate, which minimizes the load distance metric to this value, which is 71183. So your X and Y coordinates are going to be near 12 and 15. Let's see how this compares to our solution that we found using the centroid method using our formula. That was 11.5 and 13.5. So pretty close. If you look at the solution that was provided to us by the centroid method and the solution that's been provided to us using Solver. So they are close, but this is going to be optimal even more than the centroid method approach itself. I have already posted the spreadsheet online with the instructions as to what I'm doing in every step, and now you can follow me with the voice narrative as well if you want to see what I've actually done. So this is one of your questions on the assignment where you're being asked to get the optimum location using not just a centroid method but also using Solver. All right, hope that helps. Thanks.